So I was telling you that we need to evaluate the time scale of the particles, which is going to experience fluctuations in a turbulent flow. And we need to understand what will be the response of these particles to turbulence. Okay, so in this first lecture, I'm going to give you a reminder on the forces acting on these particles, and then we are going to extract from this force balance a characteristic time scale, which is going to be compared with the flow structure and the time scale of the flow structure in the turbulent flows. Okay, so that will be the second lecture, and we will see how a turbulent flow can make some unevenly distributed particle distribution. Okay, then I'm going to comment the suspension of rheology, because as you will increase the concentration of particles, the response of the flow might be different because the viscosity is going to be enhanced by the concentration of particles. And then I will switch to a different topic, which is the simulation of suspension, so computational fluid dynamics and specific techniques, numerical approaches for this simulation. I'm going to give you some examples related to separation techniques and also some of my research activities. Okay? So at any time, you may ask me a question. The way to do that is raise your hand. I come to you, you give me the question. I'm going to ask the question, so it could be recorded on the video, and then I give you the information and the answer. Okay, so but feel free to stop me and to ask me questions. I'm not going to to speak during 3 hours without any word. Okay. So that was the notes I sent as an introduction. So the forces which are acting on particles. So making a force balance is very useful when you want to predict what will be the behavior of the particles, because you need, in physics, you need equations to be able to predict what will be the response of your system. If you are able to predict, then you may be able to control, okay, and make the design. In the field of fluid mechanics, we will be interested mostly in forces related to the fluid flow, to the fluid forcing on the particles. Of course, if you have charged particles, you may have electrical forces, magnetic forces, you may have many different forces, but I'm not going to comment that. In many situations, in many separation devices, you may take advantage of these charged particles. For example, if you want to design the separation of charged particles, you may use an electric field to deviate the trajectory of the particles. Okay, but I'm not going to comment on that. I'm going to comment only the effect of the ambient flow field, which is going to generate stress along the around the surface of the particle, and this stress will give rise to a force. And okay, I'm going to comment the different forces acting on these particles. So as I told you, you may have non-hydrodynamic forces. The one that we will keep is, of course, gravity, because it's a very important force for on the particles. But I'm not going to comment the electric or the magnetic fields, which will modify the trajectory of the particles. Okay, so basically we will have two different origins for the force. The forces which are proportional to the volume, like, for example, the gravity. Okay, so the weight of the particle is the product of the density of the particle by g, the acceleration of gravity, and the mass of the particle is proportional to the volume. Okay, so as you expand the volume, you will expand the force. So this is the first type of force. It is proportional to the volume. And the second force, which is mediated by the fluid, is proportional to the surface. Okay, so as you expand the surface, you may have more stress due to the fluid. So you may have actually two contributions. One is pressure along the surface, and the other one is viscous stress. Okay, so as you expand, as you increase the surface, you will increase the response of the particle to this flow. Okay, so let's say that we take a particle of any shape. So you will have a force proportional to the volume. So this is due to gravity. And then you have forces related to stress acting on the particles. Along the surface. Okay. And this stress, let's call it T, may have two origins. One is pressure, and the other one is viscous. Viscous stress. Okay, and it depends, of course, on the flow around the particle. So when you want to make a force balance, you have to sum these two contributions, so the forces proportional to the volume and the forces which are acting on the surface of the particle. So this is what is done here on this slide. So I said that the stress, sigma n, so T is a stress, and this stress is the product of the stress tensor multiplied by n, and n is the local unit vector which is normal to the surface. Okay, so you have a surface. This surface is the surface of the particle, so you have something which is inside and outside, and n is going from the inside to the outside. Okay, so n is always pointing outwards, and it's a unit vector. Sigma is a stress tensor, and this stress tensor has two physical contributions, which are the pressure and the viscous stress. Okay. So we say that if you integrate this stress over the surface, so sigma n is a stress, you multiply by your surface of integration here. Okay, here you have a small surface, which I call ds. And if you make the summation of all these stress acting on small surfaces ds, then you will get the total force. Okay, so T, the unit of that is in Pascal. Okay, so you have to multiply that by a surface to get the force. Okay, so this is the first contribution. So the integral over the surface of the stress will give you the forces, all the forces due to the fluid which is flowing around the particle. And then you have to do the same for the force which are proportional to the volume. So F is a force density, so it's a force divided by the volume. If F is constant, like gravity, it's very simple. You can just take it out of the integral, and then you have F multiplied by the volume of the particle. So this is why I was telling you that these forces are proportional to the volume of the particle, if F is constant. So within that, you may have gravity. This is the only one we will keep, but you may have other forces like electric and magnetic fields. Okay? So let's go back to the forces due to the fluid flow. So we have pressure, we have viscous stress, and all these forces are going to be summed over the surface. And the problem is when you have a complex flow, like a turbulent flow, around the single particle, you may have a flow which is non-constant, non-homogeneous. Of course, along the surface, the stress will not be constant. Okay? And that will give you a total force and a total torque, but you don't know what is the contribution of each physical effect, because you may know that the forces which are acting on a particle is the sum of different contributions. One is a drag, the other one is a lift, the other one is added mass effect. Actually, the idea of this force decomposition is only what you want to do as a model, because when you do this integration, actually you are unable to sort out the different contributions, because you have the flow around the particle like here. So this is a picture of a turbulent flow. So you see the turbulent eddies with, you know, the white colors or the black colors. And if you want to follow one particle within that flow, you need to know what are the different stress components along the surface of the particle, and then you are going to sum up all these contributions within one force. But within that force, you have all the different effects. So you have the drag, you have the lift, you have everything. So what I'm going to try to explain you is how we can decompose all these forces as a sum of simple contribution, simple elementary contribution. Okay? When you get the force, the goal of your prediction is to evaluate the trajectory, because based on the trajectory you will be able to say, okay, the particles are going to accumulate in that part of the flow, or they are going to move in that part of the flow. So you are going to couple with the force balance, you are going to couple the second Newton law. Okay, so you are going to say that the sum of all forces which are acting on the particle is going to change its acceleration, dv by dt, multiplied by its mass. So this is the second Newton law. And based on that, this ODE, this ordinary differential equation, you can integrate in time this equation, and then you can get v, the velocity of the particle. Okay, so based on the force, you will get its velocity. And then, again, you have to integrate another equation, which is dx by dt equal to v, the velocity. And based on that, you will get x, the position, as a function of time. So x has 3 components, v has 3 components, and then you will get the trajectory. Okay, so the goal of the final goal of the force balance is to end up with a system of equations. One is the force balance. Okay, I'm going to comment on the list of forces acting on the particle. Based on that, you integrate, you will get v as a function of time. Okay, so of course v has 3 components, vx, vy, vz as a function of time. Okay, and then you have another equation which is coupled to that one, which is dx by dt equal to v, and then if you do the integration, you will get x of t, which has also 3 components, x, y, z, function of t. Okay, and that will give you the trajectory. Okay, and if you do that for one particle, it's good, but you can make it for many particles, and when you do it for many particles, then you will see what will be the trajectories of all your particles, and what will be, for example, the accumulation or the separation of your particles. Okay, so I'm going now to comment on this force, and you see the different list. This is a list of the different forces I'm going to explain, but you have to keep in mind that actually this is only done by your thinking, okay? Because when you do this integration, the only thing you can access is the total force. And we are going to say that the total force which is acting on that particle in a complex flow can be separated into elementary contributions, which are going to sum up. Okay, but actually when you do the calculation within a complex flow, you only get the total force. And you cannot, extract what is the force due to the drag, what is the force due to the lift, what is the force due to the rotation of the particle. Everything is inside your integration. So the idea of the decomposition is to say, when you have a complex flow like this, I'm going to simplify the flow as the sum of different contributions. Okay? So let's say that we have a particle in a very complex flow. Okay, so we have a flow like this, and this is the particle. I'm going to do the same approach that what you do for a function. Okay, so let's say that you have a function of x, okay, f of x. You have a function, okay, and you say, I want to know what is the value of the function here, f x naught. So you know that for a function, a classic function, a scalar function, you can make a Taylor expansion of the function, okay? So you can say that f at x is the value of x naught plus certain value multiplied by the first derivative plus the second value multiplied by the second derivative. And actually the forces that I'm going to comment is the same idea. Okay, you have a particle with a complex flow around it, and you are going to try to evaluate the different forces as a sum of contributions that you can sum up. Okay, so for Taylor expansion, for a Taylor expansion, you are going to say that this is f of x naught plus, for example, if you are here in x minus x naught f, the first derivative, plus x minus x naught square over 2, the second derivative, plus, and so on. Okay, so you say that the value of your function at the position x, the first estimate that you can make is to say that this is the value of f of x naught. If you want to be more precise, you are going to add another contribution, and then another contribution, and that for infinite. For the force acting on the particles, that will be the same. So I have a particle which is moving in a flow, and the flow is very complex. I'm going to say that this particle actually is going to experience a first effect, which is a constant flow. Okay, the flow is very complex. You have many vortices around the particles. But first, I'm going to say what is the force acting on the particle if the flow is assumed to be constant. Okay, so you see that this is similar to that. Okay, so that would be the first term of your Taylor expansion, acting the force acting on this particle as the first term of your Taylor expansion. Then I'm going to say, actually, in a real flow, the velocity profile is not constant. Okay, so what is the second term that I should include into my elementary decomposition? So I ask you a question. What would be the second contribution of a flow which is becoming a bit more complex than a constant flow? Yeah, so what would be the shape of the flow? What would be the velocity profile? What is? Parabolic. No, no, not parabolic. Parabolic is even more complex. So between constant and parabolic. What do you mean by triangular? Linear. Linear. Okay. So linear. Okay. So the second term will be, I'm going to explain what is the force acting on the particle if the flow field is linear. Okay. And that will correspond to that, to this contribution. You see, this is linear in X. Okay. And then, as you said, I can have a flow which is a bit more complex than constant and linear, and that would be parabolic. Okay, so and if the flow is parabolic, and you see that this is like this, it is proportional to the square. Okay, so the idea of building this force balance as a decomposition, as a sum of elementary mechanisms, is to follow what is a Taylor expansion for a scalar function, but to adapt this approach to the force balance. Okay, so I'm going to say that when I have a particle within a complex flow, actually it is the sum of contributions. The first contribution is the drag, because when you have a particle in the constant flow, it will experience a drag, which has two origins, pressure and viscous stress. Then I'm going to say, okay, the flow is actually not constant. It has a linear gradient. It is linear in space, like this. So what is the force due to a linear gradient in the flow? And that will give me a second contribution. And then what is the force due to a parabolic profile? Okay, so you see that we do something like a decomposition of the complex flow at the position of the particle. And based on that, we will sum up the different contributions to get all the forces acting on the particle in a turbulent flow, which is very complex because we should include all the terms. But we are not able to obtain all the forces which are acting on the particles due to the other terms. So I'm going to comment only these three contributions. Okay? So first, we have to talk about the shape, because as I told you, I have to do the integration of the stress acting on the surface, and of course it will depend on the shape. Okay, so I'm not going to comment too much on that because I know that you get already some lectures about how to do, how to build the particle size distribution, how to evaluate the shape. So I'm just going to give you 2-3 slides about the shape, because when I will comment the different forces, I'm going to speak only about spherical particles, which is the only thing we can do properly. But actually, in the reality and in the industry, the particles have different shapes, so it's very diverse, as you can see. So you may find spheres, fortunately. Sometimes we are lucky, and in the industry we have real spheres, but it's very, very rare. We may have, things like this, like ellipsoids. We may have pellets. We may have fibers. We may have stones of different size. We may have also the aggregation of many particles, and then the shape might be very complex, like fractal aggregates, very complex shapes. And for all of that, we are going to assume that we can find an equivalent sphere. Okay, so the idea is to use these forces that we know on spheres, and we are going to adapt that to particles of different shapes. And for that, we have to compare how far the real shape of the particle is from a sphere. Okay, so this is based on different criteria, like the aspect ratio, sphericity, circularity. So that will give you the feeling or a measure of the distance between the real size, the real shape, and a sphere, which will be our model shape to evaluate the forces. Okay. So if you have a sphere, you are lucky, because if you have a sphere, there's only one length scale. Okay, so you can take the diameter or the radius, it's the same, but you have only one scalar parameter to define your particle. You need the diameter or the radius, which is the same. So in that case, it's very easy, and this is why I'm going to comment that for the forces. If you have other simple shapes like disks, ellipsoids, again, it's very simple because you may have maybe 1 or 2 or 3 length scales to characterize the shape of your particles. But if you have particles like this, you may take many different length scales. Okay, so the maximum length, the thickness, you may do many things. Okay, so usually what we do is to look for an equivalent diameter because we have in mind that we want to compare these complex shapes to a simple sphere because we know what will be the forces acting on the simple sphere. Okay, so we try to evaluate an equivalent sphere in terms of hydrodynamic response. And for that, for example, we can take, if you have pictures, if you have photos of your particles, you can evaluate the surface of your particle, the projected surface of your particle, and based on that, you can evaluate an equivalent diameter. Okay, so that will tell you how big is the particle if you compare it to a sphere. So I'm not going to comment too much on that, but you know that these, so when you now have defined a length scale, okay, so it could be the diameter or it could be the length, it could be the equivalent diameter. In the industry, the particles have different shapes but also different sizes. Okay, so you have to evaluate the size. So it could be done by different techniques. You can use images like this. So if you look at these images, you can measure what will be the diameter of that particle, the diameter of that particle. You can sum up all this information and build the particle size distribution. When you know what is the size, you can make particle size distribution for polydisperse suspension. So you can make it by visualization with a microscope. You can do sieving. You can use light scattering if you use, for example, granulometry. So there are existing different techniques to give you this type of information. So you have a length scale, which could be the length, it could be the diameter, it could be the thickness, it could be the equivalent diameter. And then when you know how to define the length scale, you will get the information about the distribution of that length scale within your suspension. Okay? And of course, when we will look at the forces acting on the particle, we are going to say that this is a sphere, but it could be of different size. Okay? And then depending on the size, we know what will be the volume, we know what will be the surface, and based on that, we will know what is the force acting on that particle. Okay? So based on the information of the length scale comparable to a sphere and based on the particle size distribution, we may be able to evaluate the forces acting on different particles of different shapes and different sizes. Okay? Okay, so you see, so this is taken from a book. You see that you can find many different definitions of equivalent diameter. Okay, it depends if you do that on the volume, if you do that on the projected area, if you do it on the weight, if you do it on the settling velocity. So you may have different ways to evaluate that length. And then you are going to say that my particle, which has a complex shapes, I'm going to assume that it is a sphere, an equivalent sphere, and I want to know what are the forces acting on that equivalent sphere. Okay, so this is the basic idea. Because if you have a complex shape like this, you may need to know the forces acting on that particle, but also the torques acting on the particle. Because if the shape is complex, you need to know the orientation compared to the flow. So you need to, instead of solving an equation only for the trajectory, you need to add an equation for the momentum balance for the torque and an equation for the orientation. Okay, so you need, instead of solving 2 ODE, you need to solve actually 4. Okay, so this is 3, this is 3, so that is 6, and you will have 12. Okay, because you need to know what is the rate of rotation of the particle and what is the orientation of the particle within the flow. Okay, so for now, I'm going to talk only about spheres, but you can find in papers, and it is still under research, what are the forces acting on ellipsoids. Okay, so now we know what are the torques and what are the forces acting on ellipsoids, and then we can integrate in time the rotation and the orientation of the particle within the complex flow. Okay, but I'm not going to comment that. But you can, if you are interested, I can give you references. And it's much more complex. Okay, so I have a sphere of equivalent diameter. So for example, I take this sphere, which has the same density, but the size is slightly different to get, for example, the same terminal velocity. It's a way to define an equivalent diameter for my sphere. If I have a complex shape, like an aggregate, then you may find many more information to characterize the size of your aggregate. And this is a list of different things. So you need, for example, to evaluate what is called the radius of gyration. So it is related to the shape of your aggregate. If it's very dense or if it's very loose, you will find a different radius of gyration. It could be, you can also evaluate what is the porosity of your aggregate, because of course the forces which is going to act on your particle will depend on the porosity, because if the aggregate is very dense, the weight will be a certain value. If it's very loose, then the weight will be less. Okay? You can evaluate if it is close or not to a sphere. You can evaluate its fractal dimension. So if the shape is complex, you will find many more information on how to characterize this shape and try to evaluate an equivalent diameter. Okay, so I'm not going to comment too much on that, but you have to keep in mind that in the reality, all the particles are not spheres. Okay, and of course, the model you are going to use, even for the drag, will be only an approximation of the reality. Okay, you will have an estimate. Okay, so that was the introduction. So now I'm coming really to the purpose of the lecture, which is how can we evaluate the different forces acting on a sphere. Okay, so I'm not going to speak about ellipsoids, fibers, aggregate. I'm only speaking about spheres. Okay, and we will see if we can relate what we know for a sphere to complex shape particles. Okay. So I want to solve this equation. So I want to solve the second Newton law. Based on that, I will get the velocity, and then I will get the trajectory of my particles. Okay, and this is a list of forces I'm going to address. And these forces are related to, this type of approach. Okay, so I'm going to look at the force which is due to a constant flow field, to a linear flow field, to a parabolic flow field, and see what is each contribution to the force. So first, I'm going to talk about the buoyancy, which is very simple because it is not related to a flow. Okay, let's assume that we don't have any flow, and then we have a particle in the fluid. So we start with the very simple flow. Which is no flow. Okay, so we don't have any flow. And then we have a particle here. The density of that particle is rho p, like rho particle, which is sitting in a fluid of density rho f. Okay? So you know that, let's say this is z, and then you have gravity, which is acting on the system. So the first force which is acting on that particle is its weight, of course. Okay, so this is what is written here, mp g. So this is the integral over the volume of rho p g dv. Because this is constant, okay, g is constant, actually it's not, it's not constant. If you go very far from the Earth, it is varying as a 1 over r square. But if you do experiments on the Earth, that will be almost constant. It might vary if you do experiments at the level of the sea or in the Himalaya, but we are going to assume that it is a constant. Okay, so you can pull it out. So you have rho p g, and you have the integral of dv, and the integral of that is the volume of the particle. Okay, so if it's a sphere, that would be 4/3 of p r cubed. Okay, so if it's a sphere. If it's not a sphere, you have to evaluate the volume of your particle. If it's an ellipsoid, if it's a complex shape, you have to evaluate the volume. Okay, and that will give you rho p vp g, and rho p vp is the mass of your particle. Okay, so the first force is due to gravity. It's the weight which is acting on your particle. So I'm sure you know already that, and I didn't come to explain that. Okay, so now you have the fluid. So the particle is sitting in a fluid, and you know that when you have a fluid and gravity, the pressure P in the fluid is a reference pressure minus rho F G Z. Okay, when you go deeper, Z is becoming negative, and then the pressure is increasing. Like you are diving in the swimming pool, you know that when you go at the bottom of the swimming pool, the pressure is high and it's pressing on your ears. Okay, so it means that if you look at the pressure distribution, so the pressure is pushing on the particle. Okay, so it is pushing like this. Okay, so the pressure is always a stress which is normal to the surface. Okay, so the effect, if you have to write sigma, so the stress tensor is actually minus P, 0, 0, 0. Okay, so this is the stress tensor related to the pressure. So you see it's minus P, minus P, minus P, which means that if you take N, the unit vector pointing outwards of the sphere, P is always acting along minus N, which is pushing, it is pushing on the surface. Okay? So because we have this distribution of particle, you see that when you go from above the particle to below the particle, here you will have a pressure which is higher than here, okay? Because as you go deeper into the liquid, you increase the pressure. So the pressure is stronger at the bottom compared to the top of the particle. So it will push the particle upward, okay? And this is, and what's the name of that force that you may know? Yeah, it's kind of lift, but what is the name of the scientist who? Yeah, it's hydrostatic, but what is the name of the scientist? Archimedes. Okay, exactly. So this is the Archimedes force. Okay, so this is what Archimedes proposed, is when you have no flow, due to the hydrostatic pressure, the pressure is higher below the particle than above the particle, and then because the pressure is acting along minus N, it will push the particle upward. Okay? So this is what you get on the slide. So, so you have to sum up all the stress related to the pressure. So it's minus Pn, because it is pressing along the surface, along minus N. If you do the integral of that, so there's a theorem which is going to switch from integrals on surface to an integral over the volume. So instead of minus Pn ds, it's minus the gradient of P multiplied by the volume, and you have to integrate over the volume. And the gradient of P is, of course, constant, because the gradient of P, if you make the derivative of that over z, it's a constant. So it's rho f g along the z direction. And because that is constant, you can pull it out. Okay, so it's minus, so it should be a small p. So you pull out minus rho f g from here outside. So and then you have rho f g, and you have to do the integration of dv, and again it's the volume of the particle. So it's minus vp rho f g. And if you sum up the weight of the particle, rho p vp g and minus rho f vp g, so finally you get rho p minus rho f vp g. Okay, and these two terms are called the buoyancy force. And you see that if rho p is larger than rho f, it will be along the g direction, so the particle is going to settle. If rho p, like for a gas bubble, rho p is almost 0, it will push the particle upwards, and then it will rise under gravity. Okay? There's a warning here, because you have to keep in mind that the assumption which is behind the Archimedes force is that G is constant, that the pressure is hydrostatic. So of course it's true at the level of your laboratory when you do experiments or in the industry. But for example, if you want to know what is the buoyancy force which is acting on a balloon, let's say for atmospheric probes, the pressure in a gas and in the atmosphere is not constant. It's not hydrostatic. So it means that the buoyancy force which is acting on a big balloon which is rising in the atmosphere is not given by this formula. The effect is the same, because the pressure is decreasing as you go higher and higher, but it is not linear in z. Okay, it's not linear in z, which means that the gradient of P is not a constant, which means that you have to do the integration and you will find another equation. Okay, just keep that in mind. So you have to keep in mind that the Archimedes force is related to the assumption that the pressure gradient is constant and it is hydrostatic, and it is only true at the level of your laboratory. Okay, so this is the force. These two forces are acting on the particle due to a fluid, but with no flow. Okay. So now we are going to look at the effect of the flow. So the particle now is going to move into the liquid or into the fluid, or it's the same. You have a particle at rest, and then you have a flow. Okay, so now we move from very simple flow to simple flow. So now we have a constant flow. And then we may have two situations. One with the particle moving at certain velocity v and the fluid is at rest, or the same. The particle is not moving, but we have a constant flow. And you see that these two situations are exactly the same. Okay, so what is important is not if the particle is moving or if the flow is moving. The important point is the difference between the two. Okay, so what we need to know is what is the difference between the two. And this is called the slip velocity. Okay, so what is important is v minus u. Okay, so let's say you have a particle which is moving at a certain velocity v into a flow with a certain velocity u. Actually, the only point which is important for the drag is the relative velocity between the particle and the fluid, v minus u. Okay, so it will be the same if you have a fixed particle into a constant flow, or if you have no flow and the particle is moving. And all the intermediate situations are the same. Okay, so the important thing is the slip velocity, which is the relative velocity. Okay, and you see that in the force, in the drag, you see this v minus u, v minus u. Okay, so first estimate of that force is has been proposed by Stokes very long time ago, and he proposed that the force which is acting on the particle, so with the assumption that it is a sphere, you assume that the flow is a Newtonian flow like water or very simple liquids. I will explain you what is the Reynolds number. And then he proposed that this force is proportional to the slip velocity, v minus u, and it is proportional to 6p mu r. Okay? And this equation has been derived analytically. Okay? So this is an exact solution of the Navier-Stokes equation, which are called the Stokes equation in that case because the Reynolds number is very low. And it is an exact derivation, okay, that you can do by hand with your pen. Okay? And this is what I did to my students in the first year of class. You need 3-4 hours, but you can make it. Okay? So you have to solve the equations, and it's doable. Okay? The point is, this is a true result. Okay? There's no, it's not based on correlation. It's not based on experiments. It's all based on theory. You can write the equation, solve the equation, and get the analytic prediction that the force is like this. Okay, so based on that, we can first estimate what will be the settling velocity. And I'm sure that Professor Majumder did that. You did the settling velocity. Okay, so I'm going to redo once. So you have the Stokes drag. So we have for now we have the force mp dv by dt, and we have two forces, rho p minus rho f, vp g minus 6p mu r, and then we have v minus u. Okay, so we are going to assume that u is equal to 0. So we have no flow. I told you that this is exactly the same if we have a flow. The only thing we have to do is to keep in mind that we evaluate the slip velocity. Okay, so we have no flow. So we have a particle experiencing gravity. We have no flow, and we want to know what is the velocity, v infinite, meaning that dv by dt is equal to 0, so steady state. Okay, so steady state means that we don't have any acceleration. So we just have to balance these two forces. Okay, so you have v infinite. So v infinite would be rho p minus rho f vp g divided by 6p mu r. Okay, just take this equation. This is 0. I take this on that side, and I divide by 6p mu r. So now vp, I can replace vp by the volume, which is 4 third or p r cube. And then I'm going to simplify that. So R would be R square. And then 4/3, 6, so that would be 2/9. 2/9. 2/9 pi rho p minus rho f. And then we have R square over mu G. And this is correct. Okay. So this equation is of course very important because this is based on this equation that you can make the design of settling separators, because you need to evaluate if you have particles of certain density in a fluid of certain density, how would be the settling velocity and how long it will take for a particle to settle, let's say 1 meter, okay, which will be the size, and then there's many important applications in a gravity settler. So the important point that you can, so of course, if rho p is larger than rho f, this is positive, so the velocity will be along g, it's going down. If rho p is lower than rho f, for example, for a gas bubble into a liquid, rho p is 1 kilogram per cubic meter, rho f is 1000, so that will be negative, and then minus g will be upwards. Okay, so that will, you see that this equation is valid for the, let's say, the intensity of the velocity, but of course also the sign, if it's going down or if it's going up. Okay, but what is important is to say that it is proportional to R square and it is inversely proportional to the viscosity. So as you increase the viscosity of your liquid, you will decrease, if you increase the viscosity of your oil, for example, you will decrease proportionally the settling speed, but it is the size to the radius to the square, which is very, there's a strong constraint on that, because if you take a particle of certain size and you divide the size by 10, you will decrease the settling speed by 100, 10 square, okay? And when you go to very small particles, then the settling velocity is very, very low. You have to wait a long time, and then it's not very efficient. Okay, so this is the velocity that you can evaluate thanks to Stokes drag. So now we are going to see what is going beyond that. So when the Reynolds number is not low. So what is the Reynolds number? So the Reynolds number is a dimensionless measure of inertia and viscosity effects. So let's say so you in the lectures on fluid mechanics you have seen the Navier-Stokes equation. In the Navier-Stokes equation, you have momentum balance. Okay, so this is the momentum balance. And then you have also divergence of u, which is equal to 0, and this is a mass balance. Okay, so probably you have seen these two equations in the lectures of that was Schumann Chakraborty who did that. Okay, so you have these two equations, and the Reynolds number is. So you see that in this equation you have many terms, but you have actually two very important terms. One is this one. It is called the fluid inertia. And the other one is that one. And this is the viscous term. Okay? So now if you do the balance, because in that equation you want to know which terms are dominating, so you can make you can build a dimensionless number which is going to compare this effect with that effect. Okay? And if this dimensionless number is very low or very high, it means that in that equation maybe you can neglect some terms and make the equation more simple. And this is what actually Stokes did. So the Reynolds number for the settling particle is V infinite multiplied by its size. So we can take, for example, 2r over the viscosity. And u is mu dynamic viscosity divided by the density. So this is called the kinematic viscosity. Okay, so this is the Reynolds number, which when you write the Navier-Stokes equation, which are of course the equation you need to solve around the particle to get the flow, because the flow is passing over the particle, so there's a solution which has been found by Stokes. And he said that if that Reynolds number is very low, okay, so this is actually inertia over viscosity, over viscous effect. So if the Reynolds number is very low, it means that the inertia is very less. It's very, very, very small. And this is what did Stokes. He said, if the Reynolds number is very low, instead of solving the Navier-Stokes equations, I have only to solve the Stokes equations. Okay? At that time, it didn't call the Stokes equation, but now we call it Stokes equation because of Stokes. So you have to solve, you are going to neglect in the Navier-Stokes equation, you are going to say, because the Reynolds number is very low, the inertia is not important, so I'm going to have 0 here. And of course, the equations are much more simpler, because when you want to solve the Navier-Stokes equation, there's a term here, u gradient of u, which is nonlinear, and there's almost no solution, no analytic solution of these equations. So when you get that, you see that these equations are linear. Laplacian gradient are all differential operators which are linear. So it's much more simple to get a solution. And this is what did Stokes 115 or more 16 years ago, 60 years ago. Okay, so he solved this equation, and from that equation he found the velocity field around the particle, the pressure field around the particle. Based on the pressure, he can extract the force acting on the particle due to the pressure, but also because he knew the velocity field analytically, he was able to extract the viscous stress, to integrate the viscous stress along the surface, and finally to get the total force which is acting on the particle. And in this total force, you have actually two effects. One is pressure, and one is the drag due to the viscous effect. You have both, okay? So it means that this equation here is only valid when the settling speed multiplied by the radius divided by the viscosity has to be much lower than 1. But we don't know what it means, actually. You don't know what it cannot be 0, okay? It cannot be 0 because it would be 0 only if V infinity is 0. If V infinity is 0, the particle is not settling. So it cannot be 0. So it will be small. But what does it mean, small? Small, it could be 10 to the minus 6, 10 to the minus 3, 0.1, maybe 1 is small. 1 is compared to 1,000, 1 is small. Okay, so we don't know exactly what is the range of validity of the Stokes equation and of the Stokes estimate of the drag. And for that, you need to do experiments. Okay, you need to do experiments, and then you compare the settling speed with the Stokes estimate. If you get a very good agreement, of course, you have to keep in mind that your particle has to be a sphere. The velocity has to be constant, so you have to wait for the steady state. The fluid has to be Newtonian, and there's no effect of the wall. So it's actually not very easy to make a very nice experiment to compare with, but you can. If you do experiments, at some point you will see that the flow around your particle is not when you increase the size, for example, or if you decrease. So you see that so we can plug here the settling speed, for example. So we can write down the equation, the total equation. So you will have V infinite. So it's 2 over 9. So it will be 2R multiplied by R squared. So it will be R cubed, rho P, rho F, G over mu. Okay, so you see that this has to be much smaller than 1. So you cannot play on G. Okay, G is constant. So you can play, if you want to make it small, on the size. And it is very efficient to play on the size because you see it's R cubed. So if you divide your particle by 10, you will divide the Reynolds number by 1000. So you will reach very easily small Reynolds number. But you can play also on the viscosity. So you see it's mu square. So mu nu is mu square rho F. So you can play also on the viscosity. So if you increase the viscosity by 10, you will decrease the Reynolds number by 100. Okay? So you play on this, and you look at the comparison between the velocity of the Stokes estimate and your measurement. If you get a good agreement, it means that the Reynolds number is effectively low enough for this equation to be valid. But very soon, you will see that the flow is different from the exact solution of Stokes. So this is the flow due to Stokes. And then we are going to look at what is the effect of the increase of the Reynolds number when it's not very low. So when it's, you see, 10 to the minus, so the minus have disappeared. So here you have 10 to the minus something, 10 to the power 1, 100, 1000, and so on. When you increase the Reynolds number, we will see what is the difference. Okay, so we are going to make just a short break to